In this video, I would like to take some time to talk about plate tectonics and understand how we have all of the different surface features that we do on Earth, like volcanoes and mountains, for example. So at some point in your past science experience, you've probably heard about continental drift and plate tectonics. Prior to the 1960s, most geologists believed that the ocean basins and the continents had fixed geographic positions. And over the next decade or so, they really started figuring out that the continents were not stationary. They weren't static. They were gradually moving across the globe. They also believe that all of the ocean basins and continents were very old. Then they started to realize that there was something else at work. There was something going on that made it where these plates were not stationary, or where the ocean basins and continents were not stationary. So Alfred Wegener in 1915 proposed this idea of continental drift. He wrote a book called The Origin of Continents and Oceans, and in this book he outlined continental drift. And basically what this said is that the continents are not static, they are moving, and they have been moving. He proposed this idea of a supercontinent called Pangaea. And at about 200 million years ago, during the Mesozoic era, this supercontinent, Pangaea, began to break apart and fragmented into smaller land masses. And then those land masses drifted or moved to their current positions. Wegener and others who advocated or who supported this decision started to provide evidence for Pangaea. So now we're going to watch the smart figure about the reconstructions of Pangaea to kind of give you an idea of what these scientists were doing.
Welcome back for another smart figure. In this video, we'll take a look at the evidence
that Alfred Wegener presented for the existence of a former supercontinent that he called
Pangaea. Alfred Wegener was a German meteorologist. He's shown here in a hut up in Greenland, where he studied the weather. But he really made a name for himself with his groundbreaking idea of continental drift, the idea that the continents had shifted position over time. Wegener proposed a former supercontinent that he called Pangaea, which comes from the Greek for all the land. And Wegener's conception of Pangaea looks something like the image down in the lower right here. In the modern day, we've retained the name Pangaea, but further evidence has revealed that the supercontinent had a slightly different shape. Wegener got most of it right, but the position of Asia was a little bit off. So, what evidence did Wegener present to support this outlandish claim? Well, first off, he noted that the shapes of the continents fit together very well, almost like pieces of a puzzle. So, the most celebrated example of this is the shape of South America fitted together with the shape of Africa. The modern day coastlines are not actually representative of the shape of these two different continents. Instead, what you have to do is pay attention to the shape of the continental shelf. So when you look at the actual edge of the continental crust, even though it's flooded by seawater, these two fit together very, very snugly with only small gaps in areas of overlap. A second line of evidence came from mountain belts, modern mountain belts. So Wegener looked at the mountain belts that were present in Western Europe, in Eastern Greenland, in the eastern part of North America, and in Northwestern Africa. And he realized that you could classify these as a bunch of different mountain belts, or if the Atlantic Ocean were completely closed, one of those mountain belts fit together and they just became one continuous strip of mountains. So he suggested that these mountains were evidence that these continents were once joined along a little seam before the existence of the Atlantic Ocean. Wegener also looked at rocks, sedimentary rocks, that were evidence of different climates in the past. So if you go to Eastern North America, to Europe or North Africa or Eastern Asia today, you find evidence that in the past, in the late Paleozoic, there were coal swamps in those areas. So vast areas covered by swampy vegetation that got preserved as coal. And then in South America, in Africa, in India, Australia, and Antarctica, there's evidence of ancient glaciers. Again, the same period of time, the late Paleozoic, but these glacial deposits are spread out over all these different continents. Now, you could explain the situation here in the upper image by talking about bunches of different glaciers. So one set of glaciers in Australia, another in India, and so on, and a bunch of different swamps. But Wegener interpreted it differently. He interpreted it as during Pangea, all of the continents with the coal swamps were pretty close to the equator. And the continents with the glacial deposits were all pretty close to the South Pole. So that there were actually patterns that could be teased out of this collection of sedimentary rock data. Furthermore, the pattern of glacial striations, the scratches that glaciers leave behind, suggested that they were all part of one massive ice sheet in the past, radiating out from the center of the southern part of Pangea. Wegener's final line of evidence came from fossil organisms. This is one here. This is Mesosaurus. Mesosaurus is not a dinosaur. This is an organism that is older than the dinosaurs. It's a small freshwater reptile. You can see from the scale here in the upper left that it's not very big. It's only a few inches long, about a foot, foot and a half long, something like that. Well, you can go and find Mesosaurus fossils in both South America and in Africa. And so you can explain that distribution of fossil Mesosaurus by saying, okay, well, there were two different populations of Mesosaurus, one on each continent. Or you could explain it by saying, this is one continuous population that extended across that whole area, and then later it was broken apart by continental drift, and Africa moved away from South America. Mesosaurus isn't the only organism you can play this game with. Lystrosaurus is another example found in Africa, India, and Antarctica. Or you can even look at plants like Glossopteris, a Paleozoic seed fern, which is known from fossil deposits in South America, Africa, Madagascar, India, Antarctica, and Australia. But you could say that that's one continuous belt of Glossopteris vegetation that was only later broken apart by continental drift. That's how Wegener interpreted it. So, for review, when you look at a reconstruction of Pangea, can you use this map to illustrate the four different lines of evidence that Wegener used in suggesting continental drift? Go ahead and pause the video for a second and see if you can come up with all four, and then we'll review in just a moment.
So as you can see, Wegener didn't have it exactly right, but he backed up this idea of Pangea and this map with the evidence as you've seen in this video. So Wegener, of course, was pretty much right with his evidence and what his ways of thinking were. So he used climates, he used the way that the continents fit together, he used fossils, he used, mountain belts and different rock types and structures. And put this out, okay? In 1924, his book was translated into English, French, Spanish, and Russian. And as these scientists started to read his book and look at his evidence, as you can imagine, there was a lot of debate and a lot of criticism. A lot of scientists at the time rejected his idea of continental drift. One of the main objections was his inability to provide a credible mechanism for continental drift. So he's got all of this evidence, but he doesn't know the how, or he hasn't explained the how it happened. Wegener proposed that it could be gravitational forces of the sun and the moon, but there were some physicists of the day that countered that and said that, if there were tidal forces that were strong enough to move these continents around, then they would be strong enough to stop the Earth's rotation, and that had not happened. The other suggestion that he made is that the larger continents would have broken through oceanic crust, but there was really no evidence to suggest that the oceanic crust was weak enough to allow those continents to come through. Wegener was on the right track. He just didn't have all of the pieces that he needed in order to provide the evidence for his theory. Once we started exploring the seafloor, and this took 20 or 30 years, then we were able to kind of understand what Wegener was saying and what he was proposing. The work that was done during this time period led to the discovery of a global oceanic ridge system that goes through all of the world's major oceans. There were earthquakes that were occurring in the Western Pacific that were at great depths, more than we realized was possible. The dredging of the seafloor did not bring up any that was older than 180 million years old. And remember, we had, Wegener had proposed that these were multiple hundreds of years old. And the sediment accumulations that were found in the deep ocean basins were thin, not the thousands of meters thick that had been predicted. So this led to the idea of plate tectonics. What plate tectonics says is that we have a rigid lithosphere that sits on top of a weak asthenosphere. So the lithosphere is the layer of the Earth that is formed from the crust and the upper portion of the mantle. It varies in thickness, it varies in density, depending on whether we're talking about oceanic crust or continental crust. Oceanic lithosphere is about 100 kilometers thick in the deep ocean bases, but is thinner along the oceanic ridge system. Continental lithosphere is about 150 kilometers thick, but may go to depths of 200 kilometers or more as we get into the interior of the continents. Oceanic and continental crust also differ in density. Oceanic crust is primarily composed of basalt, which is going to contain iron and magnesium. Continental crust contains less dense granite rocks, or rocks that are granitic. So the overall density of the oceanic lithosphere is greater than the density of the continental lithosphere. And then we have the asthenosphere. The asthenosphere that you see here is a hotter region of the mantle that lies right beneath the lithosphere. In the upper asthenosphere, the pressure exerted here and the temperature here bring rocks pretty close to melting temperature. Okay, so the rock is not completely melted, but it allows it to flow. So if you think about clay or Play-Doh, when you were a kid and you played with Play-Doh, Play-Doh wasn't liquid by any means, but it was very mobile. You could mold it into, different shapes and different structures. And that's how this rock is within the asthenosphere. It can be molded into different sections and different shapes, and it can move, it can be compressed, it can expand. The lithosphere that overlies this area of the asthenosphere responds to forces acting on it by bending or breaking, not flowing. So it's much more rigid. Now, then we combine that with what we have learned about plates. So the lithosphere is broken into these plates, and that's where the idea of plate tectonic comes from. So basically the idea is that we have all of these different plates that are made up of the lithosphere. There are 7 major lithospheric plates that account for about 94% of the Earth's surface, and that's the North American that we see here, the South American, the African, the Pacific, the Eurasian, the Australian Indian here, and then all of this down here, which is the Antarctic plate. Then you see we have some smaller ones, the Cocos, the Nazca, Philippine, and so on. The largest of all of the plates is the Pacific plate. These, you can see, encompass both continent and ocean. So it's not just each of the continents, but there is ocean that is a part of these plates as well. Now, one of the main ideas around plate tectonics is that the plates move as rigid units relative to the other plates. And as they move, the distances between two locations changes. So if you have, for instance, a city on the North American plate, like New York, and a city on the Eurasian plate, like London, the distance between New York and London may change as the plates spread apart or get closer together. But 2 cities that are on the same plate are going to remain the same distance apart. Like if we had, New York and, for instance, Denver, Colorado. So this gives the idea that these plates really are moving. Some parts of some plates are comparatively weak. For instance, southern China is being squeezed as the Indian plate or the Indian subcontinent rams into Asia proper. So you've got this Australian Indian plate here. So here's India. You've got China over here. This plate is continuing to move in a northerly direction. So we get a squeezing effect that's happening here. Because plates are in constant motion, most interactions among them occur at their boundaries. And so what we're seeing in this figure are the different types of boundaries that we can have. We can have divergent plate boundaries, where 2 plates are moving apart. This results in upwelling and melting that leads to new ocean floor. Then we can have convergent plate boundaries, where 2 plates are moving toward one another. This results in the oceanic lithosphere subducting or going under the continental lithosphere, or a collision between the two that could result in mountain building. And then a transform plate boundary is where plates are going to kind of grind past one another, either the production of lithosphere, like we see in the divergent plate boundary, or the destruction of lithosphere, as we see in the convergent plate boundary. So you can see that we have, like in the Pacific plate, the majority of the Pacific plate is made up of convergent boundaries, especially if we look at the northern and the western side. But as we look at the southern and eastern side, we see that we have more divergent and transform plate boundaries. If we look at the South American plate and the Nazca plate here, we can see that this is primarily a convergent plate boundary, and we'll see that we have a mountain range that runs pretty much the entire length there of the west side of the South American continent. So this idea of plate tectonics and the lithospheric plates can really explain a lot of what Wegener could in his hypothesis, in his continental drift theory. So now let's take a look and go into a little bit more detail about our different types of plate boundaries. So again, in a divergent plate boundary, the plates are going to be moving apart. And sometimes these are referred to as constructive plate margins because new ocean floor is being generated. The two plates move away from each other, producing long fractures in the ocean crust. And that hot molten rock comes up from that and fills the voids as the crust is moving apart. As it cools, it forms new seafloor. And we get, new oceanic lithosphere that is forming between them. The majority of our divergent plate boundaries are associated with oceanic ridges, which are elevated areas of the seafloor. We have a global oceanic ridge system. It exceeds 40,000 miles across the ocean floor. And we name different parts of it. We have the Mid-Atlantic Ridge. There's a figure at the bottom of page 101 that shows you some of these ridges. It's not on this figure here, but at the bottom of page 101, you can see the Mid-Atlantic Ridge shown there for you. We also have the East Pacific Rise and the Mid-Indian Ridge as well. Then we can have what are called rift valleys. So as the seafloor spreads, there can be areas where the crust gets a little bit thinner, a little bit weaker, and we can get what's called a rift valley. Now, on page 102 in your book, there is a smart figure, 4.12. And there's a group of students there and some geologists in Iceland that explain how continental rift valleys can occur. It's a really interesting video, but it's kind of long, so I didn't want to put it here in this video. But go watch it if you have time. It's pretty interesting. Now, divergent boundaries can develop within a continent also, and can cause the landmass to split into two or more smaller segments that are separated by an ocean basin. And this is what we're seeing here in this smart figure, where we have this upwarping. So essentially what happens is the lithosphere gets a little bit thinner here. Remember, we have the asthenosphere in the upper portion here. These rocks are pretty much molten, they're flowing. And if we get a thinner area of the lithosphere, then those rocks can upwell. We can get essentially magma that can come to the surface. And this continues to melt the lithosphere. It continues to make this thinner and thinner until eventually we have pretty much spread apart these two sections of the lithosphere. And we get an inland sea, similar to how the Red Sea was formed. If this continues, then we get an ocean that forms. So we can see examples of rift valleys on continents. Like I mentioned, Iceland. There's another one at the bottom of page 103 of the East African Rift Valley. We also have a rift valley in the western United States throughout Colorado and New Mexico. In a convergent plate boundary, this is where we have plates that are coming together. So divergent, we get new lithosphere being created. But in a convergent, sometimes called a destructive margin, we get plates that are colliding, and sometimes the lithosphere goes, one section of the lithosphere goes underneath another section and is subducted back into the mantle and becomes part of the asthenosphere again. So this process of the constructive with our divergent margins and our destructive or our convergent margins keeps the amount of total surface area within the planet constant. Convergent boundaries are also called subduction zones because that is where the lithosphere is descending or being subducted down into the mantle. The lithospheric plates sink or subduct because their density is greater than the asthenosphere. We talked about that a little bit ago. So in an oceanic continental convergence, the denser oceanic slab is going to sink into the asthenosphere. This is going to allow pockets of magma to develop and start to rise up or upwell up, and we get continental volcanic arcs. So this is an example of an oceanic continental convergent plate boundary. This is in the western United States. And what happens here is that we have the North American plate and the Juan de Fuca plate. And the Juan de Fuca plate is subducting underneath the North American plate. And as this happens, and as those rocks start to melt as they get into the asthenosphere, then we can get magma that starts to come up through the surface. So it actually kind of cuts through the continental crust, and we see a continental volcanic arc like we see with Mount St. Helens and Mount Rainier, Mount Hood is seen here. And that's where all of these different volcanoes come from in the Cascades. Now we can also have an oceanic convergence. So an oceanic convergent boundary has a lot of features in common with an oceanic continental plate margin. When two oceanic slabs converge, one again descends beneath the other, initiating volcanic activity. And this is where we get volcanoes that form on the ocean floor, and we get islands that can come out of the ocean. And this is how the Hawaiian Islands were formed, the Aleutian Islands, which are part of Alaska. These are volcanoes that are found here. And so we call this a volcanic island arc or an island arc. The Mariana Islands, the Tonga Islands, all of these are formed from an oceanic convergent boundary. Most of these are located in the Western Pacific. As we know from, Hawaii, and of course the Alaskan or the Aleutians are in the Pacific as well. And we can also have a continental convergence. This is when one landmass is going to move toward the margin of another because of subduction of the seafloor. In our two examples we've had before with the oceanic lithosphere, it's dense, it sinks into the mantle, it becomes, subducted underneath another piece of the lithosphere. But continental material isn't really subducted. Okay? It is more buoyant, less dense, and so instead of one subducting under the other, they essentially just collide. And this is going to fold and deform the rocks that are found there. So in this example, we have a continental collision between India and Eurasia, and this is what caused the Himalayas. So as I mentioned earlier, when we were looking at the map of all of the continental plates, or the plates, India is essentially just ramming into China. And as a result, we get this destruction of the sediments and the rocks that are there. And as the collision continues, they just start building on top of one another and building and building and building until we have formed the Himalayas. The Himalayas are still growing. Okay. We know this, that we can measure the height of, for instance, Mount Everest, and it's still growing, albeit at a very slow rate. But you can see here in this picture, India is continuing, that Indian plate is continuing to move north. In addition to the Himalayas, the Alps, the Appalachians, and the Urals all formed when we had continental plates hitting into other continental plates. Say, well, they're not growing anymore. Correct, they're not, especially if you look at the Appalachians, because the collisions that formed the Appalachians happened so long ago that erosion has caused the Appalachians to not be as tall anymore. We can also have a transform plate boundary or a transform fault. This is when plates are going to slide horizontally past one another without production or destruction of the lithosphere. This was discovered in 1965 by a Canadian geologist who proposed that when we have large faults that connect two spreading centers, divergent boundaries, or two trenches, convergent boundaries, we can form transform faults. Most transform faults are found on the ocean floor, where they can offset segments of the oceanic ridge system that I talked about a while ago. They're part of breaks in the seafloor called fracture zones, which include active transform faults and their inactive extensions into the plate interior. In a fracture zone, the active transform fault lies only between the two offset ridge segments and is generally defined by weak, shallow earthquakes. And so that's what we're seeing here in this image. We have spreading centers, and we have these fracture zones, and along these fracture zones, we get the transform faults. And in an active transform fault, you can see that the plates are moving in opposite directions, or these sections are moving in opposite directions. The inactive zones, they're moving in the same direction. So this makes these inactive. Okay. So how do the plates and plate boundaries change? So like I mentioned, the surface area of the Earth doesn't change, but the size and the shape of the plates are changing. When we had the breakup of Pangea, it formed the Atlantic Ocean, but this didn't occur all at once. Okay? And the plates are going to continue to move over time. So this figure here shows you the breakup of Pangea. So 200 million years ago, we had essentially this one supercontinent. And as they started moving apart, we got the formation of the Atlantic Ocean. They are continuing to spread apart. India, of course, moving north into the Eurasian plate. Australia also moving north. So they're still moving, right? We're still getting some that are spread apart, some that are colliding with one another. And so we may eventually get to one supercontinent again, as shown for you at the top of page 111 in your textbook.